Hi, hi everyone. I'm Ignacio Echegoyen. I work in the Laboratory of Biological Networks in the Center for Biomedical Technology in Madrid, Spain. And I'm going to present the last thing we're working on. We work with neural data sets. We work on brain connectivity analysis, and as you might know, the first step is to quantify the correlation, the synchronization between time series. After filtering and removal, the analysis is based on synchronization. And there are many methods to do that, and all of them have their advantages and pitfalls. Some of them are based on instantaneous phases, and the measure requires the distribution of phases to follow up on message distribution. You also have information theory metrics that are based on the probability distribution, so they require large data sets, and also density estimation, which is in many times a problem. Simple correlations are linear, so in principle are not useful to analyze the neural data sets. And there are also many methods based on power spectra, coherence for example, that require also that the spectra of the time series are linear. So there are many problems while analyzing synchronization, although we have to do it to understand what's going on in the brain. So we thought that maybe we could develop a new method, a new measure for quantifying synchronization, and that it should be as cheap computationally as possible, and fast, and that assumes as little as possible from the time series, and as robust to noise as possible also. And this is the idea. We take time series, we chop them into different vectors, and we rank the values inside each vector. We compute the dot product, and we renormalize to get a value between -1 and 1. And the methodology is based first on ordinal patterns, which is this procedure of taking the time series, chopping it into vectors of different dimension, and ranking the values inside. So as you can see here, time series, we could extract a vector of dimension 3 here and rank the values inside. This would be 0 to 1, because we're ranking the values inside, and then just computing the dot product, which is kind of measure of the similarity between the vectors. And for now we are working first on Lorentz oscillators, because we can control the noise, we can control the oscillator in which we place the noise, and we also can control the coupling, so we can test which is the best embedding dimension, which is the length of the vectors in which we chop the time series. And we can also test how the measure behaves in the presence of noise, and also how similar it is to other well-known synchronization measures. Here you can see in these plots the signals, the Lorentz signals, and here we see different metrics, synchronization metrics. Our metric is the black one, and as you can see, it's very similar to phase locking value in this case. And we also tried it in magnetoencephalographic data sets. This is resting state, and it's a plot of ordinal synchronization against other measures to see how heat is related to other measures. And we are finding that depending on the dimension, we get better correlations with other synchronization measures. We are seeing this pattern again and again, which means that it's capturing synchronization, it's measuring synchronization, and although it's affected by noise, it seems to be robust. And well, this is just preliminary because we're still working on it. But if you want more details, you can go to my poster, which is number 17.